Have you ever wondered how a robot can interact safely and gracefully with its environment, perhaps even with a human, without being too rigid or too flimsy? It is a fascinating challenge to make robots adaptable. The key principles of robot impedance control revolve around actively regulating the robot's dynamic relationship between force and motion when it interacts with its surroundings. Instead of strictly controlling position or force independently, impedance control allows the robot to behave like a programmable mechanical impedance, adjusting its apparent stiffness, damping, and inertia. This approach is crucial because real-world environments are inherently uncertain and deformable. If a robot is programmed to maintain a fixed position and encounters an obstacle, a pure position controller would generate massive, potentially damaging forces. Conversely, a pure force controller might not accurately track a desired trajectory in free space. Impedance control elegantly bridges this gap by defining a desired dynamic behavior. It commands the robot to react with a specific stiffness and damping characteristic, absorbing unexpected disturbances and allowing for compliant interactions, much like a spring and a damper system. To implement impedance control, engineers often model the robot's end effector as a mass spring damper system. They then design a feedback loop that measures the interaction forces and adjusts the robot's motion or position commands to achieve the desired impedance behavior. This allows the robot to yield gracefully to external forces, like a human pushing against it, or to apply forces compliant with a surface, such as when polishing an uneven object. This control strategy is a cornerstone for tasks requiring physical contact, like assembly, grinding, human-robot collaboration, and even robotic surgery. One of the advanced insights in this field is the distinction between active and passive impedance control. Active impedance control uses for sensors and sophisticated algorithms to explicitly command the desired impedance, often leading to more precise and flexible behaviors. Passive impedance control, on the other hand, relies more on the inherent mechanical design and clever joint-level control to achieve compliant motion, offering simpler implementation but less adaptability. Understanding this spectrum is vital for selecting the appropriate control strategy for specific robotic applications. Ultimately, the benefit of mastering robot impedance control is unlocking a new dimension of robotic capability. It allows robots to move beyond isolated, pre-programmed tasks and safely engage with the unpredictable, dynamic world, paving the way for truly adaptive and collaborative robotic systems that can perform complex, delicate operations with intelligence and dexterity.
If you love robotics, like, subscribe, and keep building with us.